as we were discussing here, I don't know whether you heard us at all or not, but on Monday, our lecture is going to be online only. So for those of you who were thinking of coming to campus, my advice will be not to come to campus because we have been advised, all of the faculty, to give our lectures online. And some of the buildings will not be heated here. There is going to be a shortage of gas, so they also said. So we'll have our class. It's going to be online. For those of you who normally do this online, it's no problem. It's going to be more of the same. For those others who normally come, please do not come on Monday. Do not even drive at all to come to campus. It's going to be very dangerous. Okay. What I wanted to do is to start first of all and remind you, let me connect here to Howdy here. Go to our class. For here, you will see on, as I said before, it may look a little overwhelming on the homepage, but that's where you have everything. You will not go anywhere else. If you need anything about this class, it's going to be on the homepage. So yes, I know some people say too much on that, but well, at least that's the only one place. Otherwise, it's going to be so confusing for you to go to pages, to go to assignments, and then the whole thing. So just stick with the homepage. I have also put up the video from the problem solving session on Wednesday, and also the problems that we solved. And I have a copy of my lecture notes for today, but I will go back to the lecture notes from Wednesday, and we are going to continue from there into today lecture notes. And I will give you a quiz to do it over the weekend. It's a conceptual thing again. Do it, you can speak with your teams if they are available, as long as you enter the solution yourselves, because for Top Hat is not going like a team kind of thing. Everybody has to submit solution separately. So, but you can talk about it. This is what I'm giving you, conceptual problems, all right? Because you don't get lost into the math, but you think about the physics, and that is going to help you in everything else. Now, the one, I made a comment to the other section, and I will make the same thing again, and I will go to my notes to be able to do that, which is going to help you with the team homework. All right, if you need some suggestions there, they asked me in the other class, so I will make the same thing. So here, so let me go to my notes, and I will share the screen next. Let me share the screen. Okay. All right, so on Monday, we stopped here. I think we did not do. We stopped here. We talked extensively about the these fields from point charges, line charges, and then from surface charges. So then the next will be to go, of course, to a volume charts. Before we do that, just as a comment for your team homework. So what does the homework say? It's a conceptual homework, all right? You will not have to do math, let me tell you. I mean, it's so simplistic, the math. It's just for you to understand. I will add a page here so I can write something, a few things that will be helpful. Okay, now in that one, the homework gives you a charge. And this charge is at the corner of a cube. All right, so the cube has all faces of the cube are equal. Like this. And this is the charge. And it asks you to find, I believe, the flux that goes through one of the faces, like this one. Come right. Now, what is different in this particular point charge from what we've seen and we've talked about flux? All right. So first of all, yes. The charge, yes, the charge. You want to say something? Yes, yes, perfect. Exactly that. So the difference here, the problem here rather, is that in all of our previous cases, the charge was inside the volume. All right. So practically our volume was like that. And we define the electric flux density. So flux is nothing else but flux density integrated. All right, flux density is per unit surface in this one. So this is flux density. Now, from Gauss's law, what do we know? If we have a charge like this, the electric field lines go like that. All right, and if it's a positive charge, we'll all go out like this. Okay. And from Gauss's law, we know that the divergence of D equals Q at the charge and 0 everywhere else. All right, so because these are the divergence of D is like a differential relationship. And what did we say? The differential relationships apply at points. All right, so at the point where the charge is, the divergence of D equals Q. And at every other point equals to 0, of course, since there are no charges at these other points. Okay, and then what we do, we take the divergence theorem and apply the divergence theorem to that over the volume V. And this volume has a surface, all right? Remember, the surface is S and the direction of the surface is perpendicular to the surface and going outwards. All right, that's what we said. Now, if we take the divergence theorem, and that tells us that this divergence theorem is nothing else but the surface integral over the enclosed surface of d dot ds. And also because we have the q, which is inside the surface, and we took this relationship that gives us q. Okay, so the difference between, now this surface we took it to be spherical, but we could have taken another surface. So like another surface for q would have been a cube, or could have been a parallelogram, or could have been a pyramid or something of some sort, all right, practically. But now in the problem, they give you not the whole cube, they give you part of the cube. All right, so since the total flux is this, meaning everything, all the flux that goes out from this enclosed volume, the enclosed surface that encloses the volume, and the charge is inside. Now you have only a cube where the charge is at the corner. All right, so I could, for example, go here where the charge is, and I could have removed all of this and say, okay, now my next volume is going to be like a cube. And let's assume that the charge is at the center of the cube. Yeah. There. I would have placed it somewhere here. The relationship that I wrote here would still apply, all right? And you would know that the cube has equal surfaces. So the only thing you have to do is to go from here to this one and think what it means. Okay. Go from the center, where the case where you have the cube and the charge is at the center. And from there, try to see what it means to have only part of it. And then from there, you figure out the answer. All right. These are the comments for the team homework. So practically, these conceptual questions that I'm giving you will help you solidify some things in your mind, because they are very simple in math, but the concept is what you have to think about it intensely. And that will help you solve other problems, all right, if you solidify your concepts. All right. Any questions about this before I continue? I don't hear any questions. So now we go to the case where we don't have a point charge, which we have seen, but we have a charge that is distributed. And we took a simple case where the charge distributes evenly, all right, throughout a spherical surface. And we have a volume charge density. So instead of showing the whole charge is nothing else but the collection of all of these charges, all right, inside the sphere. And how do we characterize this charge? By a volume charge density, Q sub V. And because it's a volume charge density, the units for that density will be coulombs per meter cube or unit volume. I used meter cube here. So if I were to give that to you, I would say, well, for example, a possible charge density would have been 2 nanocoulombs per meter cube, or 2 microcoulombs per meter cube. And then I would give you all of the dimensions of the sphere in meters, centimeters, millimeters, whatever. All right. So now what I want to do is to find the electric field outside and inside the volume, outside and inside the sphere, the volume of the sphere. So first of all, I start with the outside. I do exactly what I did for the point charge. Okay. I take a volume V here, and that volume V is enclosed by a surface, which is a spherical surface, because here, since I have a perfectly spherical surface, and I have a charge distribution which is uniform, then I know that my problem has spherical symmetry. So if I know that my problem has spherical symmetry, it simplifies things. What happens with spherical symmetry? Then your quantities are functions of the radius only, but not of theta or phi. All right. So if I have 2 points here, if I have 1 point here, down here, and another point up here, there. So this is P prime, and the other was P. And if these 2 points are at the same distance from the center of the sphere, then spherical symmetry means that at these 2 points I will see the same field. So that is important to remember. Then I take this volume V, And the surface that encloses the volume is S here. And what we also see, we see that the direction of the surface is always has a direction. The direct is a vector. The direction of the surface is perpendicular to it and going outward. So it's this arrow that shows the direction of the surface. So the direction of the surface, in this case, if it is N, here, N, and here, we'll have the direction of what? Of alpha sub r, which is the radial direction in a spherical coordinate system. Okay, so then I take, as I did before, I take Gauss's law and I apply on this the divergence theorem. Same thing, all right, as before. And because I don't have a point charge anymore or a total Q, but I have a charge distribution, when I perform the volume integral, so Gauss's law, to remind you again, Gauss's law is this one. Divergence of D equals Q. And since Q is uniform, it's going to be Q inside the sphere and 0 outside. Okay, so it's going to be Q inside the sphere and is going to be 0 outside. All right, outside. Yes. The divergence of D, according to Gauss's law, the divergence of D is the electric flux density. The divergence of the electric flux density is at one point in space is equal to the Q at that point in space, if there is a Q. Now, of course, to have a electric flux density implies that you have a source somewhere. So there is a Q somewhere. Otherwise, if there was no Q anywhere, then you will not have a D, all right? You will not have a field. And D equals epsilon naught E. So Gauss's law says that the divergence of D equals the Q at one point in space, if there is a Q. And if there is no Q, it's going to be 0. Obviously, Q is going to be somewhere else. Okay. Now, the divergence theorem says that if I take this Gauss's law and I integrate over a volume, which is this volume that I selected here, volume V, then that is equal to a closed surface integral on the surface that encloses this volume. All right, here. Now, if I take the volume integral of this equation here, obviously, all right, I will take the volume integral of the divergence, but I will have to take the volume integral of the charge density. So that's why I have this one here. So as I take the volume integral here, I take the volume integral of the charge, but since the charge is only inside the sphere, it's going to be the volume of the sphere, all right, times the charge. And in fact, here I have made a mistake because that's not the volume of the sphere. The volume was of the, well, that's not the volume of the sphere. So here we go. In this one, let me correct it here. It's going to be 4 pi. How much is the volume of the sphere? 4 pi over 3. What? 4 pi r what? Yes. It has to be volume, all right? So now this is not going to change here. We are going to have a different. Okay, so 4 pi over 3 r cubed. All right. Now, and I call that Q, for example, in that case. And in fact, what I will do here, instead of calling that Q, I will change the next one. Let me just do it here so I can upload that to be correct when upload. Let me write it better. Okay, just one, bear with me. 4 pi over 3 r cubed. Sorry. I had it correct here. I was supposed to do it at the Q. One moment. Okay, here it was correct. I'm sorry. Let me rewrite it because I looked at, I confused myself out of my own writing. Okay, so let me do this following. I will erase that so we can do it all here together. All right. Now, watch what I'm doing. We have, therefore, concluded that this is true, that the closed surface integral of d dot ds equals the volume integral of q of r dv. All right. Now, in our case, q of r does not change, so it's q naught. It's a uniform distribution. All right. Now, here I explained in the above, and I will explain it. So let me just say this here, that because you're going to see it in my notes, I try to explain why I have written q of r theta and phi as q of r vector. Because if I have a point of reference here, and I have these sources, and this source can be either a collection of charges or it can be a uniform distribution, all right? Arbitrary. It could be some charges bigger, some others smaller. It could be like a variable distribution. If it's not uniform, then the distribution can be a function of location in space. In a spherical coordinate system, the location in space is characterized by r, theta, and phi. Now, I say the same thing if instead of r, theta, and phi, I give r vector. Why is that? Because by r vector, I define both the value of r, but also I define theta and phi in my coordinate system. So sometimes you will see it like this, and other times you will see it like that. And it's more concise representation, q of r vector. So that's why I would have it here. And this is in fact what shows the Gauss relation that I told you, right? It is the divergence of d equals q at some point in space, like point P, will be the q, whatever q you find at that point. And if there is no q at that point, it's going to be 0. All right. And here I just talked about Coulomb's law. So this is Gauss's law, and then from Gauss's law you can find Coulomb's law. What I wanted to write in this when you read it is to remember that you can either go and solve the problem, as I said, from Gauss's law or from Coulomb's law. The result is going to be the same, but I always go from Gauss's law because it's simpler. When you go from Gauss's law, you will always have to go through with the divergence theorem. All right, so this is a node here. So that's where we stopped. We stopped here. Okay, now that we stopped there, let me continue and say, okay, what do I have? I have to do one thing before I continue with the closed surface integral. I will have to find the total charge since they have not given it to me. So this one here is going to be equal to this volume. It's going to be this volume integral of the charge density is going to give me a total charge. Now, this one is going to be, since Q is constant, is uniform rather, so it's a constant, is going to be the volume of the sphere, which is 4 pi over 3, and then r sub s cube times q, how did I call that? Q sub v, which is constant. So this is my total charge Q. And I know what it is. If I'm outside of the volume, I know that. I know Q sub V, I know R sub S, I know everything. So then I continue. Now that I found the charge, I'm going to the surface integral. And what did I say? That the direction of this surface is along the radial direction. And since I have the dot product of D and the surface, that gives me the radial direction of D. So I have the D sub bar ds, okay, on the closed surface integral is going to be Q. But because this is spherically symmetric, what does that mean? That if I have a spherical surface that has the same center with my charged sphere, that means that every point on this surface will have the same distance from the center of the sphere, which means that every point of my surface S will have the same value for d sub r because of spherical symmetry. So d sub r is a constant. Not that I know it yet, I don't know it, but it is a constant. It's the same on the sphere, on the surface of the sphere S. So I get this d sub r out, and then I have the surface of this closed, the surface integral, closed surface integral of this surface. And that is equal to Q. How much is the area of the surface of a sphere? That is 4 pi r sub s squared. Okay, so this one is 4 pi r sub s squared. And now what do I have from here? I have the d sub r equals Q over 4 pi r sub s squared. And this is if my surface is very close, as I did it here, very close to the surface. But if I can go and find any surface which is away from it, all right? So practically, my radius of the imaginary surface that I use can be different than r sub s. And if it is higher than r sub s, then the surface of my imaginary sphere is not going to be, of course, 4 pi r sub s squared. It's going to be 4 pi r squared. Okay, so here, and this is in fact, so for this case, I will have that this one is going to be r squared, which means from that case that this is going to be r. So what do I find? I find that for r larger or equal to r sub s, I solved first before the r sub s, okay, when the two were equal. But even if when it's larger than r sub s, the result is not going to change, other than down here where r, if it's right on, if the imaginary surface that I selected is right on the surface of the sphere, it's going to be r sub s. And if the imaginary surface I selected is further away, then it's going to be over r squared. And so, yes. This r is the imaginary volume that I have for the divergence theorem, has a surface, and this is the radius of the imaginary surface. I call it imaginary because only the sphere is real, all right? I mean, the other surface, the blue one that you see, I imagine it. I placed it there to apply the divergence theorem. And I called it imaginary so we don't confuse it with this one. All right? Which means, what does that mean? That every point which is outside of the charged sphere, at every point P and P prime, outside of the charged sphere, the field changes as 1 over r squared, which is very similar to what? To a point charge. Is it not interesting? So practically the electric field outside of the sphere, or even as close as been exactly on the surface of the sphere, of the charged sphere, even on the surface of the charged sphere, and away from it, outside, it sees the charged sphere as 1 point charge, practically. That's very interesting, all right? And why is that? Because you can say, why does it see it as a point charge when I'm so close to it that I see a charge here, this part of the charge and this part of the charge. If I come here, they will have different, but they cancel out. So at the end, the field that I see at points P and P prime, no matter how close those 2 points P and P prime are to the surface of the charged sphere, no matter how close they are, but always outside, then the field there is like as if the whole charged sphere was 1 point charge at the center. That's how it feels. Now, since we saw that, let's see what happens inside the sphere. All right, that's the other interesting thing. Any questions, however, before I go inside the sphere? Any questions? Okay. Let me then here, it's just I did that, all right? I took a very weird shape and I said away from this shape. And if I am far enough, so I don't see this very much, if I am far enough, I still see like an antenna. This is very important for an antenna. Antennas change. There are dipole antennas, there are reflector antennas, there are patch antennas. But the antenna on your cell phone, here, I'm so far away, it's tiny, right? So for me, it's like a point. And so the field that I see from any of your antennas behaves at my point, at my place, as 1 over my distance from you squared. Even if your antennas may be totally different, because, for example, each one of us has a different phone, it's a different Android, and usually every company uses a different type of an antenna, and it's proprietary information. We don't know. But it does not matter. You and I receive exactly the same power, more or less. All right, that it goes as I go away from each one of you, my phone feels an impact of 1 over my distance from you squared. And that's what we were trying to explain here. Now, inside the sphere, I take my imaginary surface and volume to be inside the sphere. All right, you see the blue one inside? It's right here, inside the sphere. And the radius for this imaginary surface is r. So I apply the same thing here. I start with Gauss's law, and I apply the divergence theorem, as you can see, the same thing. But now when I integrate the charge, I integrate only what is enclosed by my imaginary sphere. And what is enclosed by my imaginary sphere is this one. This is the charge that I see. All right, this is what is enclosed by my sphere, by my surface. And then when I continue and I apply the same thing, D is also uniform on this surface because of spherical symmetry. So when I do this surface integral, finally, I find from these expressions, you see here D times the area of the surface, 4 pi r squared. But on the other side, I have the total volume, which is inside my imaginary sphere, is 4 pi divided by 3 r cubed. And that gives me then an electric field which inside the sphere increases like r. outside of the sphere goes down as 1 over r squared, but inside of the sphere increases as r until I go to the point where there is no more charge there. And if I were to plot this, I would find that. I would find that my field starts at 0 at the center of the sphere, which is interesting. I'm at the center of the charged sphere and I see nothing. Why is that? Because there is uniform distribution. And yes, every charge applies on me an electric field, but they all cancel out. So at the center of the sphere of the uniform charge distribution in this sphere, I see 0 field, starts at 0. And then I increases as I move away as my distance until I go to the edge of the sphere, the charge sphere. And then that's where it gets the highest value. And then now that I move outside the sphere, it goes down as 1 over r squared. And that's how the field is. So now what I have here, and I want you to do that as I told you, please go, and I will try to do it myself, but you also need to do yourselves. Put all of this that I'm not gonna ask you to rederive things. I want you to understand how we derive them, because then you can do some other examples yourself. But I don't want you to, I'm not gonna test you in this class. I will never test you on deriving something that we have already derived. Everything is open, all right? We're gonna have open books, open notes, open online, open internet, the whole thing. What I'm gonna test you is your ability to solve a problem, because in reality, in real life, if you go to work for a company or do your own research or whatever you wanna do your own project, nobody's gonna tell you close all of the books and go do your project. All right, they will tell you, this is the project, I want you to do it. You're gonna go to your office and you will have everything available to you. The question is, how do you use the information that is available to you to solve your problem? Nobody's gonna tell you, is gonna test you on whether you remember by heart those things. No, but we are doing these things and then you will have them available. A lot of times, it's good to have a table with things like that, so it's easy for you to use them when you need them. Okay, any questions on this? Because before I cover, I introduce the concept of a voltage or potential rather. Okay, any questions here? Any questions on those who are online? Can you guys hear me?
Not here.
Okay.
Yes.
Okay, perfect. So now I'm leaving this, which I'm gonna upload also with all of the notes. And I'm going, I'm going to electric potential. Okay. Do you remember the word potential? We use this word also in real life. We say you have a lot of potential. What does this really mean when we say you have a lot of potential? You have the capability to do something, right? You have the energy to do something. You have the brains to do something. You have the tools to do something. Not that you have done it, but you can. The same way we use the word in electrical fields. All right, so the electric field intensity, usually we use, it's an intensity, but it's in volts per meter, but we never use the word intensity. It makes it too long, all right? So we talk about the electric field. Now, we connect the electric field to a potential, to a scalar function, V. And we call that scalar function the potential. Why is that? Because the electric field eventually becomes what? The gradient of the scalar function. You remember when we talked about gradient of scalar functions and we said that we apply to, like when we plot weather and then we show the gradient. We show exactly how the weather changes. It gives you not exactly the value of the temperature in places, but also the derivative. What does the derivative tell you? Derivatives tell you how fast, and whether it increases or decreases, how fast a function changes, has the potential to change. Do you know the word derivatives in the stock market? Have you heard the word derivatives?
Yes, yes.
Yeah, why do they call derivatives? Because the stock market can go up and down. And when you see only the value and there is noise, all right, it goes like up like this. Nothing is like monotonic in real life. And then you see that with noise. At one point in time, there is information in the derivatives that say whether it's going to go up or whether it's going to go down. The derivative of a function at the point of a function tells you whether the function is going to increase in the future or it's going to decrease. And if you go to higher derivatives, it will tell you also, I mean, it gives you much better projections about what is going to happen in the future, all right? So a derivative like here, which is in space, obviously, of this function, which is scalar, is telling us of whether the field has the trend to increase or decrease, number one. The other thing that is telling us from V, which is in fact the potential, if you have like, let me give you from mechanics that you know. Do you remember when you did mechanics at school that you say that if you go higher, if you climb up on a mountain, you have mechanical potential, which means that if you fall down, you have enough mechanical energy, all right? And this is gonna, have you seen the skiers when they fall off their skis and they go down in this like extreme skiing that they do, and they go down from this kind of thing, and then some of them fall and they go down with tremendous speed. Well, that is happening because they have accumulated a lot of mechanical potential, which is like because of the height, all right? They have accumulated a lot of this potential. And the moment they lose their control, all of this potential is translating into not only speed, but also acceleration, and then they in different directions. And then you see how then all of this translates into whatever falls they have. Or if they are excellent, skiers, it becomes very high speed. They get the highest speed when they have the highest potential, when they are in the highest point. That tells it gives you a sense of how much energy you can release into some other form, all right? With this potential here, when you measure the potential, it practically, especially when you measure the potential with respect to ground, which is zero. Let's assume that we measure zero potential, like zero energy at the ground. And then you have other points that they have higher potential. In electronics, for skiers, it means you're in a much higher position, elevation. For electronics, it means that you have from zero ground, which is zero charges, you have charges. The higher the potential, the more charges I have accumulated somewhere. And the moment you release those charges, what do you have? A strong electric field. So when I say that I have a volt, I put this operates at voltage 3 volts, for example. That means that the potential in my circuits here, at the points where it's 3 volts, compared to a ground, is not there. Of course, my ground is still up here somewhere, all right? Compared to a ground, that means that those points have charges. And those charges are utilized to provide me with the electric, with the power that I need to operate this device. All right, that's batteries practically. So the potential shows how much energy I can generate. All right. Higher potential compared to 0 gives higher voltage, because we define the voltage as the difference of two values of the potential. All right, so here, for example, we will define, now that we have introduced, so potentials, in other words, has important meaning because it tells you how much capability for electric energy you have. All right, that's the word. And it's nothing else, by mathematically we define it as the negative gradient of this function that we call potential. So this is a definition. This E equals minus the gradient of V is the definition for the potential. Okay, what does that mean now? It means that if I take now these two charges, you see I have a positive, I have a negative. And obviously I have 2 points, P1 and P2. And each of these points feels an electric field, all right? So if I take any line that, if say, for example, I was another charge, okay, and I wanted to move from point P1 to point P2, I would have to spend a lot of energy to do that. Because why is that? Because I would have to fight some of the forces that those charges exert on me. That's what it means, all right? So I have to spend energy. How now here, how do we measure that? Is by taking the line integral, all right, of this divergence, of, excuse me, gradient, that product with the line which has a direction also. So I'm representing the line dl, all right, along this integral as a vector. And that gives me, on the basis of the definition, that the energy practically, or the, as I move along this line, all right, then as I move along this line, what I find is that I will have to expend energy, which is really related, we will see later, to the difference between these two values. So practically the line integral, now we say, the line integral of the electric field from P1 to P2 is nothing else but the difference between these two values. And how do we call this difference between these two values of the potential? The voltage between these 2 points. Just a second. Oh. One moment. Okay. So again, to move from one point of an electric field to another, you have to expend energy. And we will find out that this energy is related to the difference between the two values of the potential. All right. So practically you work against the forces that are exerted on you if you are a charge. And this we use quite a bit, even if in reality it tells us that the voltage is nothing else. We use it, all right? We use it. Voltage, we know about Ohm's law. We know that V equals Ri. We use it all the time, but in reality it's nothing else but a measure of the energy that has been stored in the system. And is a function of the electric field. And of course, the particular function, the mathematical function here is given as the line integral. So practically, what that means, if I know, let's assume that we have a charge which is somewhere in the corner of this room. All right, we have a charge somewhere. And we are all here other charges, all right? Each one of us has a different value. So if I want to move as a charge from where I am there, or come to another charge closer, I will have to expend energy, because I will have to fight the forces that are exerted on me. And the same thing applies to the other charges, all right? And how do I find how much energy I have to exert? If I knew the electric field that applies on me, then practically I will have to integrate that field from where I am right now to where I want to go. And that would give me the difference on these two potentials, which practically will tell me when I go and find the energy, how much energy I have to expend to go from here there. Okay. So usually a voltage, which is the difference of two potentials. See, for example, I have 2 points that are at different potential. That means that each of these points either have different charges in there collected. So if there are 2 conductors, for example, if I have 2 conductors at different potential, what it means that if I connect these 2 conductors, there's going to be a flow of charges from one to another. All right. And think of that as a skier who goes up in a mountain, and then all of a sudden, from the high potential that it has there due to the elevation, when it starts flowing down, all right, it goes down. It goes from the high elevation to the lower elevation. And of course, why is that? Because of the gravity, which is the force. Where here, we don't have gravity in our electronic system. We have electric fields, but we have electric forces. So under the impact of a force, usually if you give a path to 2 points that are different potential, you're going to have flow of charges. All right, that's why we have a current. When we say that we have a voltage of 3 volts across a resistor, what does it mean? That on one side of the resistor, I have accumulated charges more than on the other side of the resistor. And if I connect these charges through the resistor, then these charges are going to flow and are going to create a current. All right, so you have more energy on one side, less energy on the other. You give a path in between these two, and then they are going to try to equalize. So there is a flow of charges. Okay, so that's the whole idea. I'm trying to put it in those words because you have seen this before. It's just that here has more. It's the same concept, but within the context of the electric fields. And I would like to stop there for now. We will continue on Monday with this concept. I will come back and talk about this again. And I will give you a quiz, which is going to be for until Monday. And I will tell you, it has nothing to do with the voltage. It's primarily from things that we have seen. And let me connect to this. Go to here. And I have already initiated the quiz, but I will explain to you what it is. So here it is. Okay. What this one is the following. There are two functions there. One is like a triangle. The other is like a pulse, up and down. And there is one represents a field and the other represents a charge. Okay. So, and they ask you, the problem asks you to, on the basis of how these two look, to decide which of these statements is correct. Which is going to ask you, in fact, is going to, rho of x means a charge distribution, right? And E of x is an electric field. Now, what you need to remember to solve this problem is which law? Gauss's law. What does Gauss's law tells you? That the divergence of D, which I cannot write here. So the divergence of D equals Q. What is divergence of D? It's a derivative, remember? So it says the derivatives of D give you a charge. So you need to remember that to be able to find what is the correct answer here. All right, so you need to remember the Gauss's law and to translate what Gauss's law says. And that's going to help you to find the solution, okay, for this one, until Monday. If you have any questions about this, on Sunday, 1 to 3, we'll have office hours for any questions for that or for the homework, okay? Any other questions? Okay, you guys have a nice weekend.
Thank you, Professor.
Thank you, you too.
Okay, thank you.